meat of our last session, and we can come back to more hands-on a little bit. And if you have questions, do you have questions now that you want to ask? Just to reiterate some things, this is it's somewhat new, but it's also reiterating some of what we were talking earlier. I talked about how we had interest in looking at whether or not over time changes with matters or across unit changes with matters. And interest is really, really important, but interest isn't everything. What you want to study is only part of it. The approach you adopt is not just predicated on your interest, it's also predicated on the situation it's in, right? If T is small, you can't really very effectively study anything time series, right? And you can't also reliably estimate unit effects. So you have to be really, really careful. So when you have big N, you think you should be estimating unit effects is when you shouldn't be estimating unit effects. You should be doing it when you have big T. At least directly estimating unit effects. And the reverse is small, right? If N is small and T is large. And we're interested in time series issues. You need to have some time, right? So that's everything that we talked about yesterday and earlier this morning. The ADLs and the ECMs, they don't apply to panel data at all. So they're absolutely no use to your understanding of panel data. So you got your 2 time points. Just not much there, right? What can we do? Well, maybe you might be able to work with lag. Right? But what are you picking up when you do lags? You lose half of your cases, and what are you mostly capturing?
The fact that the independent variables only change on the portion of the dependent variable at T, which is not explained by the dependent variable, by the lag of the dependent variable.
Right. But what kind of effects are you picking up in the context of this time series cross-sectional stuff?
Cross-section.
Yeah. The time series measure entirely picking up cross-sectional stuff. We cannot pick up any time series stuff. How can I pick up time series stuff? You've got one observation per country, right? You can't pick up any time series at all. You're picking up this all cross-sectional, just like we just showed, right? When you drop the lag, it's the dependent variable.
What happens if you difference? You've got two cases and a 2, so you can get one case which is a difference.
Okay, difference y and difference x, right?
Okay, now you've got a difference variable which you can predict from the levels of the independent variables. Can you not do something with that?
Well, usually the approach is you difference y and difference x.
Yeah, but then you need an instrumental variable because the individual error is should still
You
be
need one more case.
So you need one more observation.
Right.
Yeah, you can't do anything without 3 cases. But amazingly enough, you can do a lot with 3 cases, over time, 3 time cases, if you have enough spatial cases.
I think the story on panel data is the way I like to emphasize it is you just can't get very fancy. So if you're dealing with small t, just be really careful. You just don't have the room, right? You consider fixed effects. We've already talked a little bit about it. You sacrifice degree of freedom to increase in efficiency. You way overestimate as a result unit effects, right? This is not uncommon. Why? Because you pick up nothing else. You're picking up measurement error, right? Sample error. This is not uncommon. I do some work on house effects in polling, like how houses differ. And this is very, very interesting. Bob Erickson and I did a paper on this a long, long time ago, because you're trying to find a way to represent preferences. We had to find a way to how do you combine preferences from different survey houses. This was a piece published back in 1999. So you wanted to be able to control for the fact that some survey houses are up here, right, 2 Republican and others are 2 Democrat, and you want to kind of get them just not because they're partisan, but because of how they weight variables and the like. And so you want to find a way to kind of put them all, sort of zero-base them so that you can actually have an indicator of preferences at a particular point in time. Mostly for us, we weren't even sure you'd have preferences at any particular point in time. You can track change over time, right? So you can at least, we don't know if we're at the right level, but we do know there's about change. Well, the thing is, when Bob and I set out to do it, so okay, so we have some survey houses that have done 1 poll. We have some survey houses that have done 50 polls. So how many polls, you include when you're estimating the effect of survey house? Right, to come up with a survey house effect estimate. Gallup's up here, Pew's down here, whatever. So how many would you think? Well, what we started with was anything more than 2. Why not, right? If we had 3, we counted at 4 or 5. We figured 1 or 2 was just too small. So we dummied up all the survey houses, right? So basically, you're just dumbing up the survey house and you're dumbing up day, right? So each day, 0, 1, 0, 1, every survey house 0, 1, 0, 1, 0, 1. And you run the regression. So you did it just with days, and then you did it with survey houses. And when we did it with survey houses, we got all these different survey house estimates. The survey houses, all the survey houses had effects, right? But the funny thing about it is the adjusted R squared went down. I'm sorry, the adjusted R squared went up. I'm sorry, the adjusted R squared went down. Our explained variance actually went down. So, and we were controlling for all these survey house effects, right? Thought we'd get a better estimate. Okay, now our error in our prediction, right, is going to be down. No, the error in our prediction, the effective error in our prediction, actually went up. Why was that? Because we over-controlled our survey house. We found a survey, three cases, right? So, you had one bad random sample issue, right? On one day, and bam, they got a -3 effect, so you have to compare. Here you got a +4 effect. -2, +5, right? So you got all these estimates. When you truncated to 5, then 8, 10, you got much more reliable estimates. You've got of house effects, you've got a better prediction over time. What's the right number? I don't know what the right number is, but one thing to do is look at your prediction error, right? It's a pretty good indicator. If your prediction error gets better, then keep going, right? So going from 10 to 9 proves your prediction error, drop. Going to 8 proves it, drop. Right? Mean squared error, not a bad indicator in this context, right? It goes down to 6, uh-oh. Now the error is going up, time to go back up to 7. Maybe we'll just pick 7 or 8. It's the same problem you have here, right? When you have small number of t, right? You're going to be subject to estimates are going to be inefficient. They're going to pick up the effects of this stuff that it shouldn't. That really doesn't matter. It's not true. Okay, fixed effects, as we've already said, introduces collinearity with independent variables, right? That move little or not at all, right? Okay. What's the other alternative to when we're dealing with panel data? There's this lag-dependent variable estimation. We started in on that too, remember? What did we do? Pretty quickly early on, we found that there's something maybe going on in our residuals, so what do? Stick in the lag-dependent variable. Isn't that how you do things? It's a common approach. Using it, you lose a lot of cases, right? One for every time series, right? One for every unit, that is, there's also a little basis for dynamics over structure vectors, right? So remember, we're talking here about panel scope. Plus estimating using LCD will pick up the effects of the cross-sectional and the time series variation, which we've already seen, right? Not just on panels. So what to do with panel data? When you have a short time series, what do? It's not the subject of this little workshop, but and as I've already mentioned, a lot of researchers, particularly those coming from a more psychological viewpoint, look at the fixed effects as really, really important as controlling for this unobserved heterogeneity, and that they will tend to advocate using them. We've got to keep in mind, they're not perfect. The X's and the E's might still be correlated. It might be time varying heterogeneity and endogeneity, and you have all this other trouble, right? All this other trouble we've already talked about in estimation. What about when you have the larger T, which is where we're really, I talk a little bit about the panel because it's hard to just jump from a single time series, I think, or a cross section, 2 time series cross section, without talking a little bit about what's in between. And we, but we're mostly interested. Some of you are stuck in that circumstance, and you want to know a little bit about what to do. And I'm happy to talk to you. I'm happy to talk more about that if you have questions as well. But I was, commissioned to do something on time series cross section, which is different, right? And this is when you could actually look at time series, right? And how do we want to go about it? Remember, when you're looking at a time series cross section, this is where you actually have a decent number of time points. You want to look at plotting. You want to plot, right? You want to look at statistical summaries of variance. We've already talked about this. Is most of the variance within, or is most of the variance between? Right? So it's a little bit different. Remember, you start off with plotting like you do with a single time series, but one of the things that you do with the time series cross section that you don't do with a single time series is you want to disentangle unit and temporal components of variance, error components, right? Basically, that's what you're looking for. You want to look at time dependency, right? This is much like what we do with single time series, and we want to do the same kinds of things. Although remember, for ELECDEMs, autocorrelation functions and partial autocorrelation functions are trickier because you need to do them by hand. And then you have, the test of auto regression, which are actually quite similar. Okay, just one thing I want to talk about. We're modeling time series. We're starting. Most people start with a very constrained model, and constrained model is when you limit flexibility, right? When you don't estimate everything. An unconstrained model, for instance, would have an intercept, which is a fully unconstrained model would have an intercept for every unit, right? It would have an intercept for every time point. It would have a coefficient for each x, right, for every unit. People could even start about talking about having coefficients, right, for different x's at each point in time, right? That doesn't get a lot of discussion, does it? After all, cross-sectional effects of x can vary across time, right, as well. Just as unit effects, x can vary across units, right? If we could expect random coefficients across units, why can't we have random coefficients across time? Right? We would also allow for variation in the autoregressive parameter, right? The errors, if it's like at points in time. So that's a fully unconstrained model. We're going to start here with a very, very constrained model. This is where you assume most of that heterogeneity away, right? You just focus on modulating x and y. It's assume a nice little rectangular data structure. And I just want to talk a little bit about a couple of things here. One of the things that happens in time series cross section that you that you oftentimes encounter are unbalanced panels or unbalanced time series. You know what these are, right?
Well, let's give an example. Studying elections across countries, some countries have more elections than others. Some countries have elections every 3 years, some countries have elections every 4. Malta has elections every 7. The United States has elections every 2. What the frigging heck do? You go half the time distance for some countries than for others in order to get the same number of elections? Do you skip every second election? Do you have an unbalanced series? Mostly we have an unbalanced series.
Right. Now the problem with those kinds of things too is you don't really have, they're all measured at different points in time, right? And so you don't really have common time points. Right? So that messes with it. But let's say you have we started measuring, in the case of the European Union, some people entered early into the country, right, into the Union, and some countries entered late. And so you have, some longer time series in some countries than in others. This is not a major problem if there aren't major asymmetries, right, in the balance, and because data can handle that, most statistical routines can handle that. And there's just this form of computation that are used. That I'm not going to get into a whole lot there. I just want you to know that, so it's up front. And if you're
actually, Stata does this really nicely. SPSS, you're dead. In R, you have to work really hard. Stata just does it for you.
Well, in R, you have to tell it what to do.
Yeah.
So Stata does its program to do that. And it does it in ways that strike me as sensible. I didn't look at it, I'm not a student of what's inside Stata algorithms, but it strikes me as pretty sensible. And people who actually do know what's in Stata algorithms, I spent some time at College Station with some people who do programming for some of this stuff. We actually talked about some of these things that they don't have. And College Station, Texas A&M, in Texas is where, it's kind of interesting is you run into Stata programs out running and, just stop it, and a guy, was walking his dog and we started talking and I was, oh yeah, I'm here in Philadelphia, it was interesting, what do you do? I was a statistical program, what do you do? Oh, I'm a programmer for Stata. And I was like, oh, really? So it's, well, yeah, we said, oh yeah, this neighborhood is not hard to run into one of us. It's not a big place, So I did ask him, I think, he looked at me strangely when I asked him about it, like, why are you talking to me while I'm on my walk? Just because I'm a programmer, that doesn't mean I want to talk about it all the time. I mean, they're not academics, right? We're a little bit stranger than they are. So anyway. Okay, so then once we've got the data set, right? So we've got this data set, and you want rectangular data set. You've got all the cases filled in, or they're unbalanced, but it's not in a wacky way that's going to worry you when you go proceed to imputation. So then you've got to get the, what's next, right? Like any kind of model, you've got to make sure you've got the right x variables, right? And you've got the right functional form. And these two things constitute specification. Functional form is important. Remember when we were going through ADL and ECM, the whole point of that discussion was about functional form, right? And if you recall, that discussion didn't go really deep into functional form. We didn't have all kinds of funky polynomial, representations, right? We were just talking with very basic ones. Mostly because it's oftentimes hard to separate out the basic from the fancy, right? Even when you have decent time series. That's oftentimes going to be even more true when you're dealing with time series cross-section stuff. So you have your rectangular matrix, you're pretty happy, your data set, you're pretty happy with it, you got the specification right. Then the next question is, do you have the Gauss-Markov assumptions, right? That, you're mostly interested here, pretty not very worried about residual means being 0, but you might be a little worried about uncorrelated, right? And heteroscedastic, correlated heteroscedastic errors, right? But if you are confident, right, that's what you have, right? Then you can go to OLS. Everything's done. You can just not worry about pretty much anything else. But if the answer to no is you have, right, then you have manipulations recorded. Okay. Beginning with stationary data, right? The main issue here we have is autocorrelated errors. Time series issues. Identification of the problem is the same. The solutions are too. Right? Here's the classic GLS approach. You run OLS, you take the residuals, right? You regress the residuals on the lag residuals and all X, and you test the significance on the lag residuals. The usual alternative modeling approach, right, is what? Lag dependent variable, right? You'll model y at time t as a function of y at t minus 1 plus x. Okay, these two approaches are similar, but they differ in one important way. It's the effect of lag x. And this kind of goes back to this discussion we were having about, remember, when we had the lag-dependent variable in the model, and we estimated the autocorrelation parameter, we got kind of a wacky coefficient on the lag-dependent variable. We went from positive to negative. One thing you have to keep in mind is that if the lag-dependent variable contains the lagged x's, right, and the lagged errors, right, the serial autocorrelation is only going to be focusing on the lagged errors, right? Right? So what about x? Lag x does not matter there, right? Y is a function of x, and if there's serial autocorrelation, lag e, right? Here, y is a function of x and lag x. Why? And lag e. Because in here is x 2 minus 1 and e 2 minus 1, right? In fact, you just write an equation, right? What's y 2 minus x? Everything gets lag, right? 2 minus 2, x side 2 minus 1, and e 2 minus 1. And so these are two very different approaches. One's a dynamic approach, and one's really not a dynamic approach. Right? As we've already discussed, right, this one, with the AR1 approach, y reacts to x, right, and then the effects of the errors decay off. In the lag-dependent variable approach, y adjusts geometrically, right? equilibrates. Remember we've gone through this before?
Went through this yesterday, that's
Today's trip. It's the effect over 1 minus the lag parameter. Remember, so 10 over 1 minus 0.8 was 50. But why would you expect there to be differences in the effects of x and the residuals, the errors? I mean, if your errors are ignorance, right, then you'd expect no difference at all, right? X and the unmeasured x, right? You have the same, x1 you have, x2 you don't have, x5 you don't have. But if you did have x2 and x5, wouldn't you expect it to have the same decay rate? Or would you expect it to be different? Maybe your thinking is, maybe measurement error has a different decay rate, right? After all, wouldn't we expect measurement error maybe to look more like a moving average process and the effects of x variables to look like an error process? Well, okay, if we have a perfectly specified model, and the only thing left in our error term is measurement error, right? Sampling error thing. And so we expect that to come and go. So actually, yes, Chris, I expect there to be different decay rates for the y's and d's, for the x's and d's. But remember, the great thing about the augmented Dickey, the autoregressive distributed lag, is that it allows for both possibilities, as it includes the current x in the model and the lagged x in the model, right? You have the current shock, and then what can you do? You could go look for autocorrelation in the lag shock, right? The lag residual. It's fine. You don't need to settle it by its own. You don't have to pick one or the other. Run this. It's the flexible solution. If you run that, and you find gamma equals 0, then what do you say? Well, that goes to 0. That looks like a lag-dependent variable model, right? If, on the other hand, it's minus beta, right, times that, then we end up with an AR process. Why is this the right value? Does anybody know? A Turkish coffee for anybody who can get it right. I always go to my same shop. Oh, that's where locals go, so it's good.
No takers? Hey, real Turkish coffee is on the line.
I think it's 3 Turkish lira. Just think. Nobody wants to try. Well, where would this come from? Well, this is this coefficient multiplied by that, right? And the only time you're going to multiply that times that coefficient, right, is when you're referring on that variable, is when this is when you're looking at the lag, right? So if you're looking at if this is beta p, right, minus beta p, then the lagging of that will wipe it out, right? So we're subtracting that right out of the model, so it's gone. And then we'll be left with just an AR process, right? Where it's just that. Basically just taking out the passive from this, right? The passive piece is gone.
Keep that slide. Put it up in the lights over your bed. You need to be able to do that computation preferably in your head. You know, what is the relationship between the beta on the lag and the phi? Because that's where the dynamics are.
Yeah, so just taking there's nothing from the past, right? Here, it's just the only thing from the past is there. Right? It's basically that. So anyway, that's a useful. It's kind of useful things. I mean, ADLs. Here's the ADLs, kind of nice, right? Again, I mean, ADLs really, really easy to interpret. Here's a little bit of explanation.
end of the day.
That's too late.
With the algebra in my head, yes.
The rest of you? Susan, you hanging in there? Is there any line? As regards estimating, the reason why these are, this is what most people do, right? You want to just correct the GLS, I want to correct the serial correlation, I want to go on, I want to do lag dependent variables, but again, you shouldn't do that. You should just go up here. You should just estimate the ADL, just right there, right? And then what you're going to do is just, and it'll tell you whether or not it's a lag dependent variable model or a serial correlation. If you do get, as regards this generalized least squared AR1 approach, which again is focusing on the errors and the lag dependent variable, which is taking both the lag x's and the lag errors and assessing their persistence in the future. The difference really matters little when the effect of lag of y is small. This kind of makes sense, right? As there's little difference between the immediate impact of x and the long run impact of x, right? Do you understand why that would be? So, when this is small, right? Say this is like 0.1, right? That's really small, right? What's the long run impact here? What's the long run effect of the long run equilibrium? It's b over 1 minus 0.1, right? Which is what? B over 0.9. Which is basically b with a little bit at there. Not much difference. If that's 0.9 though, b over 1 minus 1, right? Sorry, 0.9. B over 0.1. That's 10b. Right? So as b shrinks, the difference between these two specifications is really small, not to worry. As phi widens or increases, the difference is widened, they get huge. Right? When phi approaches 1, neither approach is correct, right? Because you have a unit root. Because now you have a unit root and now you have non-stationary data. For those of you who've been sticking through with me for the last 15 minutes, this is really good because we started with really easy stuff, the same kind of stuff, and now we're kind of coming at it from a different point of view.
Can we get rid of the stuff that's taking up space at the top of the screen?
Oh, no, sorry. Is that better? Any questions on that? Susan? Okay. It's not that, shouldn't be that tricky, right? It makes sense, right?
But notice, there's no such thing as XT arena. If you want to talk about stationarity, if you want to talk about AR processes, if you want to talk about moving averages, you've got to do the all the hard way. Which is why you need to understand what arena is doing. You can't just treat it as a black box when you have cross-section data.
Yeah, remember when this goes to 0, right? It's not a whole lot difference at all, right? Actually, no difference. When it's low, you have very little difference. When it's high, you have a big difference, right? Makes sense, right? If your model is an AR model, you don't have any y's in it. When you have a little bit of y, t minus 1 in there, it makes a little difference. When you have a lot of y, t minus 1 in there, you have a big difference. So it's kind of, bigger has bigger impact, right? Smaller has smaller impact. It's very, very highly intuitive. There's a math to it, but it's highly, highly intuitive as well. You don't need to, again, you don't need to remember the math. Although this is really useful to always keep in mind. It's this little equation for the equilibrium. Okay, so what do you do with non-stationary data? This is difficult. The same problems apply when you're dealing with non-stationary time series cross-sectional data as apply when you have a single time series exactly the same. Though the solutions are less developed. Mark tends to be a step ahead of me on these kinds of things. Almost all of the work in the area focuses on single time series. Almost nothing is being done and has been done looking at time series cross-sections. Right? And the common approaches that have been developed that we've already discussed, one is a differencing approach, right? Which is the ARIMA. Get rid of all the integration, right? The ECM approach is model, right, the process, explicitly model what's going on. Right? This throws away information, this includes some. And remember, this is also perfectly compatible with using an ADL. Remember, although it's going to be less explicit about this kind of equilibrium stuff that would interest you if you're doing, if you're working with non-stationary data. So you might want to model it more explicitly, right? And that's what was recommended with non-stationary data, as we've already discussed, right? There it is. You've seen this equation before, yesterday, today, and now again.
But the difference now is that there's an I there. The I is different for each panel. So we're modeling each panel separately and reporting the result as a single result. Which means that, for instance, if you have a unit root in one panel and not in another, you're dealing with it. You're dealing with it where it exists, and it's not causing you any problem where it doesn't exist. This is because of cross-section time series data that I'm so hot on error correction models.
Well, right. Yeah, I tend to not model them separately, but you can, right? And this is another element of heterogeneity, right? Is what it really is. It's just adding another parameter. Or combining them differently. If you need to, telling whether or not you have a different error correction model is a hard thing to do, because you have to be able to say you're speaking about the relationship among multiple coefficients, right? I mean, is your equilibrium between x and y the same, right? Which means is the B3 the same? Then you're going to ask the question about also, is your error correction rate the same, right? Is it decay or the same? And then you have this current effect the same. So you're asking for comparing it across different panels is hard, because you're comparing not just one coefficient or one solid statistic. You're trying to compare multiple coefficients. Ideally, you don't have to do that. This is hard to do, and it's hard enough to do time series cross section when you start partitioning. The more heterogeneity you try to estimate, the harder it gets. Just trickier. Particularly when you go into the Bayesian world, because then you have to, you're oftentimes putting priors, and those priors need to come from somewhere. So this vector prior, the bigger the vector, the harder it is to be sure you're right. Okay? Oh yeah, just remember one thing, if x and y are not co-integrated, right, one's only modeling short-term changes in y, as a function of short-run changes in x, right? So there's no error correction. That's a repeated multiple times. So it sort of could devolve to an ARIMA model, right? And B2 drops out. Okay. So what are we going to summarize here? When you're dealing with time series cross-section data, which means these are not panel data, right? These are data that allow you actually to look at things over time, right? Not just cross-space them a little bit over time. Those assessment approaches are identical to the ones you would use with a single time series, which is part of the reason why we spent a good amount of time on that, right? There's no difference whether you do it for single time series or multiple time series. It's the same. The T is really, really limiting. This is also true, right? This was true of a single time series analysis. It was true of a panel, pool cross-section time series analysis too. When you have a low frequency T domain, there's little you can tell about the dynamics of the variable, right? Whether in one country or 50 countries. How do you diagnose it? Do the same way you do, right? The Lagrange multiplier test is sort of the best general test. That's why it's highly recommended now more than the Durbin-Watson, because you can do the Durbin-Watson with the Lagrange multiplier. You can't do, the big higher versions, more lags with the Durbin-Watson. It's limited. If you're dealing with stationary data, right, you can assess specific form. For instance, a lag-dependent variable or an autoregressive process, right, using autoregressive distributed lag. I'll show you. You don't have these slides to hand, but I'm around. You can probably hand stuff. Pretty much always with the shot of email. And if it's non-stationary, as we already discussed, or possibly non-stationary, looks like it could be, might be theoretically or empirically. Yeah, I really believe it's non-stationary. Even though the stats aren't making it obviously clear, I'm going to go on with an error correction model. Right? Or I believe it's stationary, but the stats look like it's non-stationary. Damn it, I'm going to use an error correction model. Right? Just basically, just do it if you're at either one of those conditions. Right? Okay. So what about estimating cross-sectional unit? You find so far, right? What about estimating these cross-sectional unit effects? One of the classic approaches to dealing with panel data, right, have been estimating fixed effects with lag-dependent variable, right? So it's an LDB model. So you have y equals a function of yt minus 1 plus x sub t, right? Not xt minus 1, x sub t. And then adding in these intercepts for countries, for these units. This introduces bias. We've already talked about this, right? Remember we talked about the bias you get from doing that? We talked actually sort of about it indirectly. If you don't have unit effects and you estimate a lag-dependent variable in a model, what do you do? You, to a large extent, pick up unit effects in your lag-dependent variable coefficient. So it's less indicative of what's happening over time, more indicative of what's happening across units, right? Particularly to the degree of the variation across, expand the variation across units, right? Drive up the effect of the lag-dependent variable. What we're thinking about here is something that's kind of related to that, but a little bit different. And we're wondering about, okay, when you put in these unit effects, not when you take them out, when you put in these unit effects, what are you doing to your lag-dependent variable coefficient? And here you're biasing it downward, driving it down. Partly from that same effect, right? Partly. But partly because it's a function of the t. The bias, we know this is a really neat little finding called Hurwitz's bias. We know that the bias is going to be 1 over big T. So for instance, if you have a T of 3, you're going to bias down 3 time points, and you estimate a lag-dependent variable model with units, dummy variables, or d-mean. What you're going to basically be doing is you're going to be reducing your estimate on the lag-dependent variable by 33%. It's a huge reduction. The great thing about it is if you're working on, which is why another reason, don't get fancy with panel data. Be careful with panel data. Now the bias disappears as t increases. Why? Because it's 1 over t, right? So if you've got 30 time points, what's the bias? It's small. So it's a 3% bias. That's okay. Instead of a 0.92, I get a 0.89, 0.9. I'll live with it. 100 points. Rounding error.
There's 2 things about this bias that you have to bear in mind. One, if you are looking for an effect of your lag-dependent variable, because theory tells you it should be there, and you've got a short time series and it doesn't come up significant, that could be because of the bias. Okay? So basically, you risk a type 2 error when you say there's no effect of your lag-dependent variable. That's one consequence, one reason you might be looking at this. The other is exactly the opposite. If you think there shouldn't be an effect, and you find that there isn't an effect, you could be wrong. Maybe there really is an effect that you would be seeing if you had a longer time series. Those are the practical realities of the situation with this bias.
Yeah, you know when somebody says, you know, the statisticians say the asymptotics are generally better, which means the estimator performs better, right? The estimator performs better in T, as T increases for fixed effects. Okay, so it's a big problem for panel. It's not a big problem for most time series cross-section stuff, right?
Yeah, it starts to be a problem when you get below about 6 cases. You know, we are not so accurate in our measurements that we're going to care about a deviation of less than 5%. But when you get below 6 cases, now it's starting to be, and I think this is one of the reasons why they say you can't do TSCS with less than 6 time points. I mean, that's, they used to say 10, now they're saying 6. I don't think we're ever going to see them say 5. You know, 6 is achievable. It's not so hard to find a series of panel data that has 6 time points. And it's becoming easier as we go forward in time because more and more surveys are being conducted, more and more data is being collected, and because time is moving forward, we're getting more and more readings across time. There's lots of instances now where we have 6 time points or more.
Yeah, I mean, you still have the problem with the unit effects being overestimated, right? You still have that. I mean, with 5, 6 time points, you know, those estimates are going to be affected by random fluctuations in a way that an estimate based on 12 cases or 15 or 30 cases would not. So you haven't solved that problem down there. You're not so worried about, I mean, you may not worry so much about the lag dependent variable and the unit effects in there, but you still got to worry about whether or not your unit effects are going to make it hard for you to find the effect of your X row. Most of you are not doing these analyses to get lag dependent variable coefficient just right? That's going to be part of the story. That's going to give you part of the equilibrium, right? It's going to give you part of the process. You also want to know, most of you are interested in the X's, right? That's why you're doing work, this research. Is I want to know how my X affects my Y, right? Every conversation I've had with you outside, I've had about 5 conversations now with people outside, it's all about X's and Y's. It's not about lag Y. Nobody's once asked me about lag Y.
They should, because the X feeds through the lag.
Well,
If you don't take account of that, you're underestimating the effect of your X.
So now I expect more questions about lag Y. My answers oftentimes involve lag Y, but the questions oftentimes don't. So far, so good on this? Now with small t, so that's large T, we want kind of large T, right? Yeah, ST, the last sentence is about that. As T increases, as T gets large. And so it's not a problem for time series cross-section, and time series cross-section is defined as when we get T large, right? When panels define when T is small. Again, Mark is very much correct in emphasizing that there's not, you know, there's not these false, I don't like these false cutoff points, you know, like it's 30 cases, the central limit theorem's okay, 29, oh my god, no, I can't do it. Okay, with small t, you have a little alternative, right, to random effects, right? And this is the same if the independent variables are constant or near constant, right? So this is TIV variables are slowly changing variables within particular units. Many of you, and I've talked to a number of you for whom this is true, will have both small t and variables that don't change much over time. So that's where you're most likely to end up working. Now, so you'll be dealing with random effects. Does that solve the problem? It's what you're going to need to use. Does that mean those results are pure? Random effects a solution, or the solution, or is it just sort of a second best? You seem like you're just poised to say something, but fighting.
I don't want to say like best or something like that.
How about second best?
Least worst?
Least worst. Good, okay. But it's leaves problems on the table. Like what? We talked about them already, but I'd like to hear somebody say them back to me. Well, what's the main problem? When you don't properly control for unit, fully control for unit, I guess is the best way to think about it, fully control for unit effects, what's the problem? Remember, when you're generating the random effect estimates, you use the rows based on a first stage equation that has dummy variables in it, so you make sure those residuals don't have any unit effects in them, right? Remember, the x, if the x's, right, and the unit effects are uncorrelated, we're fine. Are the x's and unit effects usually uncorrelated? No. Most of us don't think they are going. Remember those Kennedy equations I showed you on the board? Right. X's and the unit effects were correlated, right? The correlations between the x and the unit effects were very different to the correlations between the x's and the y's within the particular countries, right? Remember, they were 0 for the 3 countries within. They were positive across. They were positive within the other example, and negative across, right? Right? So we can't solve that problem by estimating random effects. That problem is still there. You say, oh, but I don't have any choice. I don't have big T. What am I supposed to do? Estimate random effects, and then put a big question mark next to your results, right?
And always calculate between effects as well as within effects, as well as the random effects. Because if they're really different, you need to learn. You know, there may not be an answer. If they're the same, you're fine. That's worth knowing.
Yeah. Okay. Now, if your data are multi-level or effectively multi-level, you probably are okay with random effects. As useful to thinking of time series models in this way, and Marco hinted at this, as you can think of yearly data as being nested within countries, right? If you have country data over time, you're getting multiple observations from within a country, right? So your time is kind of within the country. Now, with time series cross-section, the difference in some senses is that you would expect that these observations may be connected, right, over time because of their dependence, right, on each other. So it's not just a matter of there being some kind of unit effect, right? This is an actual effect, right, of y on y, right, over time, which is important. And you could assess this, right, to some extent, and that's you know, that's mostly going to be a thing. We're not going to do too much on that today. But okay, in contrast with fixed effects, right? Remember we said fixed effects, the asymptotics are, right? Sorry, are the best. Remember we said for fixed effects, the asymptotics are best in T for fixed, right? And for random effects, the asymptotics are best, sorry, this typo there, are best in N. They're best in the cross sections. So as N increases, you get better estimates, right, using random effects. That's partly because you get more variance, right?
One thing that's really important to know, nobody will tell you this except me. As far as I know, nobody's discovered this except me. Panel-corrected standard errors are the standard errors you get from random effects. They are identical. When Beck and Katz wrote their article for the APSR, they may not have known this, but they were confusing the profession enormously by telling us that panel-corrected standard errors were something new that they had invented. They maybe were something new that they had invented, but they already existed and had been invented long before by somebody else because they are identical to as many significant digits as you care to look at to the standard errors that you get when you use random effects. So you don't have to say to yourself, oh my goodness, should I be using random effects or should I be using panel-corrected standard errors? Thank God they are the same. The profession doesn't seem to know this yet. And I think that Beck and Katz are reluctant to let us know it. for whatever reason. So we're sort of stuck in this situation where we don't know something that's staring us in the face, at least. But if you use the same data and you countercorrect the standard errors, and then you do random effects, you'll see that they are the same. So it doesn't matter whether you think of your data as a time series or whether you think of your data as a hierarchical model. The way the calculations are done are identical.
Yeah, we're gonna have to go. I mean, they come out similar to me, but not quite identical. But I think it may have to do with specification. I specify those things. But they're really.
You have to use MLE.
Yeah, they're really.
They're not the same with ours.
They're really. Yeah, they're really. So. Yeah, well, maximum likelihood. That makes sense given what they do, right? That would make sense. Now, remember when you're estimating random effects, and I'm reiterating some stuff, but it's coming in a slightly different sequence here, so that's why I'm reiterating it. It seems the right thing to do here, right? To remind you of what we've already discussed, that when you're doing random effects, you need to worry if there's a difference between GLS and the MLE estimation. You really need to expect to do both, and trust the MLE if there's a difference. Not that it's necessarily right, but it's more likely to be right than the GLS approach. Okay. I mean, remember, if people sell you these solutions are surefire, then it might make you feel better, right? But it doesn't make it right. So just the world is, there's loads of uncertainties. We'll get to that. Okay, and always buyer beware. We've already emphasized this. Using random effects, there is no avoiding the possibility that not estimating fixed effects produces biased estimates. Right? There is no avoiding it. I have this paper with Stuart. I'll hopefully be publishing it soon in a special issue, and hopefully we're right. Giving the alternative to using random effects, and this is what economists would probably say. Don't publish it. Unpublishable. Don't research things you can't use fixed effects on. Why are you doing it? It's really important. We have enough data. It's a really important question. Institutions, representation, public responsiveness, big questions. Can't do fixed effects. Go study turnouts.
Well, it might turn out that you're wrong. And in which case, somebody in 5 years' time gets a great article disproving you. But you still get cited.
Probably not going to be in 5 years. You need to get some time points, right? The nice thing is I'll be really old. By the time I won't care. Probably like the attention, actually. When you're 75, you're probably just happy that anybody's reading your stuff, right? Right? I mean, you'll be there one of these days, I hope. I won't. Okay. On estimating the effects of TIVs, we're going to spend a little time on this, then we're going to take a little break, then we'll come back, we'll do a little bit more talking, and then we'll do a little bit more hands-on. And then I think we'll probably end about 5 o'clock. Is that a good time, Susan? People early. I have some appointments with people scheduled. I'll have time, if we do that, I'll have time to slot somebody in earlier, between 5:15 and 5:45. Okay. Before we take a break, I want to just do this a little bit on TIVs and slowly changing variables. Are any of you familiar with some work that Plumber and Schroeder have proposed? Okay, well, this is a real problem area. This, because as it's obviously you can't obviously estimate fixed effects and the effects of these variables that don't change, right? So
time invariant variable.
Right. Or but slowly changing ones have the same problem. Random effects is what you're dividing, but it has its limits. We've already discussed that. Now, there are some alternatives to random effects, and one is an instrumental variable approach, which is associated with Hausman. It's a pretty popular name in this stuff. You probably have come across this name. There's a Hausman test on comparing whether fixed effects or random effects are the right estimation approach. There's also this multi-stage approach, which is associated with some political scientists, Looper and Chucker, right? Okay, like is what is common among political scientists, and I'm friends with these people, but like what is common with political scientists getting into the methods business, they're getting banged around pretty badly. Some of you may have noticed the whole political analysis special issue dedicated to smacking them around. They got a lot of attention. They got response. I think their approach probably took a hit, though. It was burning through the scholarly discipline like wildfire. Citations were run amok. In fact, William Green, one of the critics of the issue, started the piece off saying this approach is everybody's using it, and wait a minute, we better hold your horses, hold on there. Let's take a look at what they're doing. Okay. The instrumental variable approach is a pretty simple one. It's just like an instrumental variable approach to anything else, and what you do there is basically find instruments for the variables and a change, right? And there's a problem to this, like there isn't any instrumental variable solution, right? It's it's a solution, a theoretical solution to many issues. But there are problems. There's always problems. You need to find the validity of you need to find valid instruments. That's a big question mark. That's really hard always, It's just, and then you have to be able to determine that they're exogenous, right? And that's really also hard. So one of the problems with using instrumental variables, the disentangling endogeneity, is precisely that. Questions about their exogeneity. So oftentimes you're finding really the emphasis typically in that circumstance is what? Find exogenous variables, which oftentimes turned out to be not very valid instruments, right? That's the sort of circumstance you face. It's the same problem when we're dealing with this here, right? So it's just exactly the same kind of problem you find in the rest of the statistical world when you're dealing with these these time series cross-section models. Okay, what is this is the Plumper and Troger, that's the P&T. They invented something called fixed effects vector decomposition. Probably not the catchiest phraseology, but fairly descriptive of what they're doing. And it caught on, right? So the acronym didn't, and the wording didn't get too much in its way. And this involves taking your dependent variable, right, and regressing it on time varying variables, right? So your x's that actually change over time. And also fixed unit dummies. So you got a regression. Y sub I sub t regressed on x sub I sub t, right? Plus dummy for unit 1, dummy for unit 2, dummy for unit 3, dummy for unit 4, and so on. Right? Then you take those dummy variables, right? The coefficients on those dummy variables, right? And you regress those on the TIVs, right? To isolate the residual part of the unit effects. So what you have here is this other part of the unit effects, that's residual part, that's unrelated to the TIVs. Then you take the TIVs and the residual part, and you include them in the model, right? Replace the dummy variables with those two components, and then you estimate the model anew. Here it is, y regressed IT, regressed on x of IT, right? The TIVs, and then the residual dummies, right? So now you've basically taken each dummy variable and partitioned it, right, into two components, right? And then you want to see what is the effect of this TIVs. So you're basically trying to see how much of the unit effect is due to the TIVs and how much is due to something else. Right? Okay, this is kind of a clever thing, right? But it has been challenged, as I said. And it's been challenged because it's not clear at all that it's different from a least squared dummy variable approach, which involves you simply just putting in the dummy variables, right? And you can see that, right, as I was walking you through it. The way I walk you through it here, it should be kind of clear. You're wondering, wait a minute, how exactly is this different? And that's the problem with it, it looks like, according to some people. It relies on certain assumptions which are that some people say are untenable, and its asymptotic properties are not at all well known. It's understandable because it's a new approach, right? So it hasn't been fully vetted. So, while this is going to be touted as, this might be touted as the solution to dealing with time invariant and slowly varying independent variables, don't count on it. Okay? So it doesn't look like it maybe is a solution that is a universal solution, and that what we might find ourselves having to deal with is at least in the short run until something else comes up, is random effects with the knowledge, right, that there is no avoiding the possibility that not estimating fixed effects produces bias estimates.
But in the long run, we have longer time series. You know, so this is a problem that's going to fix itself over the course of your lifetimes.
On that upbeat note, do you have any questions? Just drink a lot of carrot juice, run. You'll get a lot more. Yeah, a lot of you smoke. I mean, that's.
Yeah, that's scary.
That's
I
right.
once read the riot act to my students at the EUI. You know, why am I dedicating myself to teaching you all this stuff when you're just going to die of lung cancer?
We're going to have some seriously unbalanced panels before long. So why don't we have some coffee, have some drinks, continue laughing, and we'll see you in about half an hour or maybe another hour.